Hi everybody, it's Mrs. Dinkelman, and we're moving on to Unit 12, which is about parametric equations. And I'm going to lump vectors in there because a lot of what we need to know calculus-wise is very related. So basically everything that we have done, and not everything, that we learned in regular like function mode, we're going to have to learn how to do in parametric equations. So just a couple of things. First of all, on your calculator, if you want to be able to graph parametrically, if you go to mode, that very first thing, so right now the graph is in function mode. That's normally how we do things, but there's also parametric, there's also polar. Sequence, I actually have never played with that. 3D is three-dimensional, so they'll give you formulas for X, Y, Z there. And then differential equations, you might have played with that before. That's actually a slope field grapher. So if you ever wanted to graph a slope field that way, I kind of forget that it's in there, but that's what that one is for. So we're going to go ahead and make sure that we put ours in parametric if you're going to use this calculator. I'll also show you how to do it in on Desmos as well. Don't forget on the 89 to hit enter twice to make sure that it's in the right mode. Okay, so you'll notice here now our equations say xt1 and yt1. So what we need to have here is we need to have an equation for x and an equation for y. So it is as if x and y are kind of independent from each other and they depend on this parameter t, which a lot of times is time. So what can happen then is we can figure out what's happening horizontally versus time, and then vertically versus time, and then where the particle would be when we consider both. So let's just go ahead and graph this on our calculator. So t, so again, notice we have to use t's, which is why there's t's up here ready and available, so that if we're graphing in parametric mode that we'll have those. So I'm just using what's here as an example, and we can graph that. I'm just going to go ahead and see what kind of zoom I'm in, something weird. So let's go ahead, and I'm in a zoom standard, and then we'll kind of check out what happens there. Oops, I accidentally hit pause. So we're given just this amount. So there's a couple things that we can adjust. So let's take a quick peek at the window. So this is saying that time, or t, starts at 0. So t doesn't always have to be time, but it can be. And right now we have basically 2 pi as the other end. So we could up that a little bit and see what happens if we go to 10. Let's just look at the graph real quick and see what happens. So it got a little bit longer, like we got a bigger picture there because we allowed time to be bigger. So it just kind of depends on what you need there. T-step. So this is really your calculator is taking data points every, in this case, 0.13, whatever that number is, and it's plugging in a point and then it's connecting the dots. So if we made this, let's say 0.5, what should happen is we notice the graph gets graphed a little faster, but it might be a little bit more pixelated. Notice how maybe it has a little bit more almost like steps in there. And then if we go, let me go back to the window and change that t-step. If we change it to 0.01, it might be too long, but we'll just go ahead and look. It's going to take a lot longer to graph because it's gathering more and more data points, but it'll make that smoother curve. Just kind of by the way, anytime your calculator is busy, you can hit the on button and it will stop being busy. It won't finish what it's doing, but it'll at least stop being busy. Okay, so that's just graphing in on the calculator in parametric mode. On Desmos, so I happen to have that available as well. What we would have to do is we would have to graph as if this were a point. So we're going to go square root of t for the x coordinate here, comma, I think it was 1 minus t. Okay, and then you can see that little part on there, and it also has a parameter for t, so we could change that if we want. We could also add a slider for t and kind of see what happens as time goes on. In fact, if you're in my class, we'll do like a racing bugs, and then you can have a slider there so you can see what the bugs are doing. So anyhow, that's how to graph then on Desmos, so make it kind of an ordered pair. Okay, so this first section in parametric equations is just about the basics. So a lot of what we're going to talk about in this particular section is not necessarily on the AP exam. I just want you to have a good hold of what a parametric equation is, how to deal with it, what to do if you get stuck, how to graph it, and to do all of those things. And then the next section will finally get to the calculus part of it. So if we want a graph, we could, if we have a calculator, obviously we can use that if we want. If we don't have a calculator though, we can just make a table of values. For my brain, I kind of like it have it tilt on its side, but I didn't do it that way. So I'm just going to plug all these time values in for the x first, and then I'll do the y. So the square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. So in my mind, I probably wouldn't really want to plot these two because I'd have to estimate where they were on the graph anyhow. Okay, so now the y coordinate, 1 minus 0, 1 minus 1, 1 minus 2, 1 minus 3, 1 minus 4. Oops, I better actually do that right though. I said 3 and then didn't write the right thing. 1 minus 3, and then 1 minus 4. Okay, and then we literally plot those on the graph. Now the disadvantage of graphing in this way is that once we plot this, it's going to, it's kind of not going to look parametric anymore. So let's see, a 0 and a 1. So we can't see time happen on a graph like this. And let's see, I'm just going to skip to that last one, this 2, -3, because that's just the one that makes the most sense in my brain. 1, 2, 3. So what we do a lot of times on a parametric graph that we've graphed, that was a terrible way to connect dots. I'm going to try that again. What we often do to indicate like what direction this goes in so that people can see that it really did have movement even though we can't really show that is they'll put an arrow like this. And I'm not going to put an arrow down there like it goes on forever because it might not. I might really only want the graph until time is whatever, 4. Let's say 4 seconds in. So I don't want to indicate that it goes on forever, but I want to make sure that people know that this thing kind of goes in this direction because that's how the points kind of came up as time increase. So it's helpful to have that time increase as you're doing that one. We confirmed that one already. Now, one of the things they might ask us to do is eliminate the parameter. So that's eliminating the t value so that we can figure out what was this in like regular coordinates. So I'm just going to come back up here to do that just so I can have this. So I think it's going to be helpful here maybe to solve for t. So if I square both sides, I get the value for t, and then I can come over here to the y equals and say, oh, that's 1 minus x squared. Which let's just take a quick peek at our graph that we did and say, oh yes, it does look like an upside down parabola. I don't have the full picture because I don't have something going on the left-hand side because I just made time start at 0. So a lot of times just read into what they want you to have as far as time. So on the assignment, you can just kind of pick that time 0. I'm just letting you pick a few here to look at. Definitely feel like you can use the calculator to double check and do all of that. This is when we're going to eliminate the parameter and make sure that we can get those to see what they would look like just as x, y Cartesian coordinates on Cartesian equations, or sometimes called rectangular equations. Okay, get going on that.